All right. Thank you very much, Alan, and thank you, Representative Beyer. It was great to have you as part of the event. We appreciate your comments very, very much. So, welcome to the last session of the day and the last session of the conference. This session, called It's My Turn, Collaboration and Coordination of Ground and Space Telescopes, is generously supported by Northrop Grumman. Thank you very much, Northrop Grumman. With a limited number of data collection platforms, how do we prioritize who and what studies should come first or should get more time? The panel in this session will discuss the tools available now or coming soon and explore how best to collaborate to make best use of their time and capabilities. With that, I am very privileged to introduce our moderator for this session, John O'Meara, Chief Scientist at the Keck Observatory. John, welcome.
Thanks very much, Jim, and thank you to the sponsors and to the AAS for organizing this wonderful set of conferences. I hope we can do it all in person next time.
Agreed.
Okay, so I think if we could bring up the slides, and if we could go to the next slide, I'd like to introduce the fine group of people that are with me that I've known for a number of years. First off is Ashlee Wilkins. She's professional staff on the House Space Science and Technology Committee. We just heard from Representative Beyer, who's on that committee, who chairs that committee. We've got John Arenberg, longtime friend of mine and Chief Mission Architect for Science and Robotic Exploration at Northrop Grumman. Heidi Hammel, who is the Vice President for Science at AURA and an interdisciplinary scientist for the James Webb Space Telescope. And some fool in the hat, that's me, John O'Meara. I'm the Deputy Director and Chief Scientist here at the Keck Observatory. So next slide, please. I'm going to trivialize the next 30 years of ground and space-based astronomy and distill it all into one single question. And that one single question that I think we're going to be tasked with answering in the next few decades is, how did the universe enable biology? Next slide, please. And we heard a wonderful panel about exoplanets, but I stipulate to answer that key question, that grand challenge question for astronomy and astrophysics. It's not just this, it's not just the exoplanet point, even though that's a critical part of it. Next slide. It's also this. To be able to understand how the universe enables biology, we have to understand the universe from its very first moments, the very first structures to form in the universe, to understand the formation of galaxies, how the galaxies take in, process, and expel their gas to form stars, and that's what's shown in the upper right-hand corner. We need to understand how stars form. We still basically don't understand that at its very root level. And we need to understand how planetary systems form, and we need to understand the full diversity of exoplanets, and indeed the inner parts of our solar system as well. If we're really going to be searching for life in the universe, we have to look way out and we have to look within our solar system. And next slide, please. To be able to do that, we need the most powerful tools that we have, and the tools cross the entirety of the electromagnetic spectrum. And relevant to this discussion, they're on ground and space. So we need flagships. We need the next great suite of observatories to complement the ones that we have now. We have Hubble and Chandra now and many other great observatories now, but we need the LUVOIRs, the HABEXs, the Origins, and the Lynxes of the future to really understand all of those processes. But we also need a balanced portfolio. We need CubeSats to develop and extend new technologies. We need small and medium class missions to do focused studies and surveys. And critically on the ground, we need large eyes on the sky to study the sky en masse, which is the Rubin telescope shown above. And we need very powerful eyes to look very deep into the universe, to follow exoplanets, to follow the first structures. Next slide, please. And it will also need these. This is the era of multi-messenger astronomy. It's no good to understand galaxies and the impacts of gravity without going after gravity itself. We'll need to understand gravitational waves. We'll need to have multi-messenger fields like neutrinos. And critically, more and more over the decades, we're going to need robust ability to simulate these phenomena in giant computer simulations to really test the theories and push them beyond. And finally, as an anchor point, we're going to need our best and brightest. And that means a truly diverse workforce in both academia and industry, working together across the spectrum of talents that we have here in astronomy. Next slide. And critically, we need coordination. We're still a pretty siloed field. We like to think about ground-based astronomy and space-based astronomy, and it's time for us to really leverage all of those things together to go after this key question. And so today I'd like to ask the following question. Next slide, please. And this is the thing that I'm posing to our panel and hopefully have a little discussion in Q&A, which is in terms of ground space coordination, it's what the science requires to be able to go after this question. It requires this kind of coordination, but it can be hard to enable and often very difficult to achieve. So next slide. That leads me to asking the question, what are the primary barriers we have for ground and space coordination, collaboration, and how do we remove them? And so that's the question I'm posing to the panel. And I'd like to turn it over, next slide please, to Heidi, who is going to be giving us some examples and some barriers on ground-based and ground and space-based coordination. So Heidi, off to you.
Thank you very much. If I could have the next slide, please. This is an example of coordination of ground-based and space-based observations working together. On the right-hand side, you see a beautiful Hubble image, and you also see superposed at the Northern Hemisphere some Hubble ultraviolet images showing you the aurorae of Jupiter. And so this is a classic case of what Hubble can do as a space-based observatory. But on the left, you see the same planet, but observed with the Gemini Observatory on Mauna Kea in the infrared. And the planet looks very different because you're sensing a very different part of the atmosphere. In the infrared, you are sensing through the cloud tops that you see in the Hubble image down to a much deeper part of the atmosphere. And the bright areas are where the atmosphere is clear, so you can actually see the warmth from the deepest layers of Jupiter's atmosphere emerging outward. So this is a classic example of how you use these ground and space-based observations in tandem. But this is a high atmosphere and a deep atmosphere. And what about the middle atmosphere? We've got that covered too. In the next slide, you can see some results from the JUNO spacecraft, which is in orbit around Jupiter right now. And the JUNO spacecraft with radio waves senses the middle part of the atmosphere. So coordination of ground and space-based telescopes are crucial for getting a holistic view of, in this case, Jupiter's atmosphere, but I'm using this as an analogy for many other kinds of scientific endeavors. I'm very familiar with planetary ones because I'm a planetary scientist, but the same type of coordination of ground and space is crucially important for many, many kinds of astrophysical and other planetary examples as well. So what are the barriers to this? This looks great. Next time step. This is, how do you get there? Well, if I'm a scientist who wants to study Jupiter, I have to support myself via grants. And if I want to get observing time on Hubble or Gemini, I have to go through a time allocation process. And if I want to have a spacecraft mission, that sometimes takes years to develop. It's a completely separate part of what NASA does than what Hubble is. And all of these have to work together. And if they don't, you get into double jeopardy or triple jeopardy, where you may have observing time, but no data, no funding to analyze it. Or you may have funding, but you get shut out by the time allocation process. And the timescales don't work together either. And those of you who are listening to the previous panel about exoplanets, you heard this articulated explicitly by some of those panelists saying, there's this problem of the, timescales aren't commensurate with the funding and the applications, et cetera. So these are some really pretty significant barriers. And all of this only works if you have facilities. The next time step is a reminder of that. We had Hubble, we have Gemini, we had JUNO. Well, let's look forward in time and ask about sort of the future. Let's talk about in the next time step, let's talk about that big question that John articulated and that you heard a whole panel discussing, the exoplanet piece. And before I do that, I have a really short digression. Next time step, I want to talk about why not just study Earth, if we want to learn about Earth. Earth's so important. Planetary stewardship is crucial. How do we connect planetary science to stewardship of our Earth? And to answer that question, I'd like to introduce in the next time step and here, my cat, my cat Metatron, who's sitting here enjoying this talk. I love my cat loves me. If anything ever happened to my cat, if he got sick, or if he was ailing or something was going wrong, I'd want to take him to a vet. But I wouldn't want to take him to a vet that has only ever studied one cat, even if they studied that one cat in meticulous detail. And the same is true for planetary science. We learn so much more by studying the full panoply of planets that we have. And you heard this in the exoplanet discussion. So the next time step, I would want to take my cat to a vet, not only who studied just the Earth, but also a Jupiter and a Saturn and a Venus and 5,000 exo-Earths. That's how we understand the broad suite of planetary science. And you heard that echoed in the previous panel about exoplanets. Okay, so with that digression, I want to turn to this question of exoplanet observations. So the next time step, the National Academy of Sciences, working with the community, put together a strategy of how to study exoplanets. And this is one of the seminal figures, and it's way too complicated for me to go into in like the 5 seconds I have left. But what I want to do is in the next time step, illustrate that there's 2 regions that actually need to work together to really allow us to fully characterize this field. And in the bottom in the blue, it talks about space observations, and circled in the green above is Earth-based observations. And so the next time step, these are the facilities that you heard John mention. We're talking about extremely large telescopes in space. We're talking about extremely large telescopes on the ground. And this is truly what we need to fully characterize all of these exoplanets. But we'll get into some of the barriers of this a little bit later. My last slide in my little introductory session is that even when we build these, next time step, we still will have the, oh, I forgot, I have this, this is one of the main barriers to building these large telescopes. This incredibly complicated system is a cartoon that represents how do you build super large telescopes. Even if our decadal survey in astrophysics comes out in a month and says, yes, build these supergiant large telescopes. That doesn't get us from the bottom left with our decadal survey to the bottom right where there's money to build. We have to go through a very complicated process with our funding agencies and Congress. And the little yellow boxes are where the astronomers slot in, but you see there's a whole lot of other things going on, and they're all very important. And this is a big barrier, not an insurmountable barrier, but a barrier that requires a lot of coordination of many different communities. So the next time step, so even if we do survive that, and in 15 to 20 years, we have these fabulous new facilities flying, the final time step is we still have to solve that problem that I mentioned before about the double jeopardy, when you have to balance time allocation, building the missions, and how do you support your scientific community and have it all work on the time scale to enable the science that we want to get out. That's a solvable problem too. Next, that's the end of my introductory remarks.
Thank you very much, Heidi. And we're going to loop back to Heidi, who might be able to bust the occasional myth in some of these barriers in a bit. John Arenberg, let's go to you, please.
Thank you, John. I took the approach to imagine my phone ringing, and it was John O'Meara speaking for the science community, saying, John, we want to cooperate across the realm of astronomical instruments to do the best job for science, and we want you to do the design. So I did what I usually do and try to scope out the problem. What are the flavors of the problem? So let's move on to the next slide. And what you see is a family tree of cooperation with some examples. So let's put all of these systems under the guise of cooperative systems. We can do this together synchronously or asynchronously. Asynchronously means we looked at the same object at the same time. This could be an archive search. This could be calling up your buddies and say, how about you point your system at object X. And this could have happened in the past, the long distant past. This is pretty easy, right? This doesn't require time. This would be an archive search. If we want to do it live, so to speak, there's two ways, two flavors of that. I'll call it scheduled and ad hoc, where ad hoc is driven by the universe, could be alarm driven. John mentioned multi-messenger. I wrote down a couple, I left off neutrinos. Sorry, I'm an engineer, not a scientist, but gravity waves, gamma ray bursts, supernovas, other temporal cues that are not a priori mentioned. So you can imagine a giant clearinghouse, the world astronomical community saying, hey, go look at that. And then there's the scheduled types of observations. And then they also have two flavors, casual, and I'll call them intimate, where casual, again, is there's this event that is known by either mission design like L-Cross, that was an impactor on the moon, or by good old-fashioned physics, the collision of Shoemaker-Levy 9 with Jupiter that everybody coordinated in a very simple way, and everybody pointed their instruments to observe that. The other, I'll call it an intimate connection, essentially where you form a ground space system of systems. And the best example is an idea that's being worked on at Goddard by John Mather and Elliot Peretz and a large team of which I'm a small part of. And this is a remote occulter. So this is a huge starshade that works in coordination with a ground-based telescope. So the next slide overlays essentially a view of, are these single instruments, are these independent instruments, and it gives you another layer of looking at this kind of cooperation. Next slide, please. So we can imagine, the architecture of this coordination. There's some kind of message with being sent to the cooperating systems, and then they can either fulfill this request or not. So on the technical side, there's really questions of what's the required latency? How fast do I have to steer the Keck telescope off of what it was doing to get the optical cohort with the gamma ray event, et cetera, et cetera. And some of these systems can do it, some of them can't. What is the science priority? Let's say John is doing a high priority observation on the ground and the alarm comes. You have to decide ahead of time whether you're going to slew the telescope or your spacecraft away. And then finally, there's all the regulatory, contractual, bureaucratic, and organizational concerns that go with it. So on the next slide is an example of some ideas I put forth at a workshop that was done at Goddard to how to organize the cooperation between this large starshade and a ground-based telescope. And you need very low latency, and it's clearly a bespoke solution. But the fact that we could even draw a system diagram tells us this is simply a hard engineering problem. It's not a problem of fundamental physics. So the technical side, we can come up with alarms, we can come up with these kinds of bespoke solutions. So I'm fairly confident that given time and no bureaucratic barriers, we can make this technically work, essentially an integrated global astronomical system. Next slide, please. So, at the 2-minute of analysis level, it seems to me that the hardest problem here is the non-technical hurdles. The precursor to that is the scientific community having the imagination to think across these lines and say, hey, funders, hey, engineers, if we could coordinate, this is what we could do. So it's not just the exoplanet pop, it's we could solve gravity waves or gamma ray bursts or other cool things along the way. What's the value proposition? How do we organize ourselves? How does the scientific community set those priorities? Then call the engineers and we'll figure out how to put a phone, in every observatory and say, point your telescope there. So while the technical aspects are going to be hard, they're not the hardest problem. And I think that's my last slide, and I pass it off to Ashlee, who's going to help us solve the hardest problem.
Yes, thank you, John. I am, as the panel's resident policy person, and this first round, I wanted to just give very 101 level overview of the federal policy and governance sort of landscape. Much of this, I'm sure that many folks on this in this audience know, but just to make sure that we're all on the same page and to sort of identify some of the, I might not say barriers, but part of the world that you do have to encounter and navigate in order to get to the kinds of goals, the really exciting science and facilities goals that you've heard folks already outline. So next slide, please. So we have just again, very 101 level, we have on one side of the world in federal, at least on the federal government, you've got the executive branch, which is governed, of course, by the White House, by the president in the White House. That decides policy, or that sets policies for the agencies that we know and love, DOE, NSF, and NASA. I mean, today we'll be focusing on I would say probably more NASA and NSF, but DOE is also a provider of many astronomy facilities and partners with both agencies, both NSF and NASA, on coordinating some observations. The White House has a number of its own offices that are look at interagency and multi-agency issues. The most important ones, I would say, for the science agencies and for astronomy would be the Office of Science and Technology Policy, or OSTP, and then the Office of Management and Budget, or OMB, which works with the agencies on developing their annual budget proposals that you hear about every year. And the executive branch is governed by both laws, by statutes, of course, but also regulations that are written within the executive branch, and policies. And those can be defined at either the agency level or government-wide. So sometimes there are policies, particularly when it comes to, say, personnel, that do have real impacts on the conduct of science. Those might be not a NASA policy, but they are in fact government-wide. They are from the Office of Personnel Management, for example. And then next slide. Of course, on the other side, you have the legislative branch. So this is where I live, or where I work. We have the House and the Senate, and we usually categorize, I'm talking about the work that the House and the Senate does in this space, as either part of the appropriations process, which is the annual money, the annual budget process, or by authorizers. And authorizers are the agencies, or are the committees and the legislative activities that set policy and do oversight. There are ways that those two worlds can get blurred a little bit, but that's the sort of general scheme. In the appropriations world, the House and Senate have parallel structures. So there's a single appropriations committee in each of the House and Senate. They have subcommittees and NSF and NASA are funded under the Commerce, Justice, and Science subcommittees. DOE is funded under the Energy and Water subcommittee. And this is the same in the House and the Senate. In authorizing world, it's a little bit more complicated. On the House side, you have the Science, Space, and Technology Committee. That's where I work. I work specifically on the Space and Aeronautics subcommittee. So we have NASA and essentially all of civil space activity. But then on the Senate side, and the Science, Space, and Technology Committee also covers NSF and DOE Office of Science. While on the Senate side, this is split up a little bit differently. They have the Commerce, Science, and Transportation Committee. And then they have the Energy and Natural Resources Committee. And similarly, and this is not necessarily fully comprehensive, but similarly, Congress had, to the executive branch, Congress has committees that look at government-wide policies. So regulations and oversight for issues such as cybersecurity, regulations for acquisition, procurement, contracts. Those can be government-wide, and those are handled by other committees, but of course can have significant impact on the agencies that we're talking about today. And then next slide, please, or time step. And then I just wanted to also mention, again, it's not comprehensive, but there are a lot of inputs, official inputs, in addition to the many stakeholders who provide input to these processes. But there are many advisors and assessors who give formal advice and help conduct oversight for the activities of the executive branch and provide that information for Congress or for the executive branch. You've got the national academies. Of course, the National Academy of Sciences was created by an act of Congress signed by President Lincoln to provide the nation's scientific advice. In this context in particular, you have the committee that John O'Meara has been chairing, the Astronomy and Astrophysics Advisory Committee, that looks at the intersection of the three agencies and where they overlap and where the gaps may be. In the legislative branch, we have the the GAO, the Government Accountability Office. Every agency has its own inspectors general. You have FFRDCs like the Science and Technology Policy Institute or Aerospace Corporation. And then of course the agencies themselves have advisory committees at the top agency level, but also down to at NASA, for example, each of the science division has its own distinct advisory committee. And so those provide advice that we in the legislative branch pay attention to, and they have provide advice directly to the executive branch. And so I'll stop there, and I think we're moving to our second round.
Okay. Thanks very much for that, Ashlee, John, and Heidi. And right before we start to talk about lifting some of the barriers and really enabling significantly improved ground space coordination, I wanted to make just a couple of observations, which in general don't have to do a lot with money. Actually, they have to do with cultural approaches towards a lot of these things. And then I'll loop back later, just give quick musings in a couple minutes on how I think we might get rid of some of these cultural barriers as well. So next slide. The first observation I'll make is that the philosophy of the agencies that enable and often fund astronomy do not in general overlap. This is done by design. NASA is mission focused, NSF is science focused, for example, of the two agencies there. DOE builds large facilities to do experiments and has very different sizes of the teams that participate in these things. And these different philosophies really go at the problems in very, very different ways. And so coordinating the assets that those agencies enable is oftentimes difficult by design, not because they want to hamper coordination, but because what drives them at a mission level, at a fundamental philosophical level, is very different. Next slide, please. The other one is that the reward structures within astronomy, within academic studies in astronomy, don't necessarily align, right? In particle physics, it's very common to have a paper with 3,000 authors, and somehow those people continue to flourish in their environments, get jobs, become professors, lead their field. But in astronomy, we're transitioning, we're in that tough transition period between the lone visionary who goes out and writes the nature paper that changes the world, and then the giant teams that are going to be able to be needed to use these massive facilities and to coordinate them. How do we reward somebody who gave up telescope time on the ground to enable a discovery from space and vice versa? Right now, the reward structures don't necessarily align, and they certainly don't align for a lot of the aspects that build those facilities or that enrich those facilities, either with software infrastructure, physical infrastructure, things like that. And that's one barrier to actually coordinating these things, is how do you reward the people who are in it? Next slide, please. The third is that ground space coordination is usually viewed as a set of trees, not a forest. By that, I mean, we take an observation with, say, Hubble on the ground, and then Keck follows it up. That's not viewed necessarily as an ecosystem where those two are constantly interacting back and forth in the way that John was alluding to with something like a ground space system with an occulter. That's a constant feedback loop that we don't in general do. We do it a little bit in transient astronomy, quick follow-up, but that's not really coordination. Again, that's more of a, one tree is announcing I'm a tree, and then another tree says, okay, I'll look at you, but it's not really viewed as an ecosystem and as a forest. And next slide, please. The last piece of culture that I'll mention is that Rosetta Stones are hard to find and some are kept hidden. What I'm talking about here is data. Right? There are exciting new mandates coming out of all the agencies around open data. But right now, if you were to ask for the data from the Hubble Space Telescope and the data from Keck, right, those are in wildly different formats, which means that you have to be the translation layer. right? It is not presented in a common format where we can go straight to the science. And that's a hamper to coordination, because if we constantly have to be translating this language to that language in terms of the data, the ability to go straight after the answer, the science, is somewhat hampered. So for our next round, next slide, please. What we're going to do is now try to look at breaking some of these barriers and busting some myths. So for a few minutes, each of the folks will use. I know Heidi has some slides and I have a couple of quick slides. We'll try to keep it to a couple of minutes so that we can have some time for Q&A at the end. So next slide, please. I'm going to switch over to Heidi. Heidi, next slide.
Yeah, thanks. If you could do the next slide, please. John said he looks to the scientist community to have imagination of what they want. We have plenty of imagination. I can imagine 15 years from now, we have a brand new suite of tools. That logo that you see on the left that says Remain in Light, that refers to a constellation of great observatories in space, not just a LUVOIR, but also a HABEX, also a LYNX, also an Origins, to do the full multi-wavelength spectroscopy and imaging of the universe like we did in the early days with Hubble and Spitzer and Chandra. I can imagine that, John. We also imagine these very large ground-based telescopes working together, whether it's the giant Magellan telescope or a 30-meter telescope. I can imagine that too, but there's this barrier that we can't afford it. And so I want to just address that very briefly. The next time step. This is a classic NASA sand chart, and everything up to about the year 2025 is directly from NASA. So I'm not making that up at all. After 2025, I am making it up. I'm saying if we keep doing the things we're doing, including lots of small missions, explorers, CubeSats, probe missions, double the probe budget, have lots of billion-dollar class telescopes. What I'm saying is that if we don't change the budget at all, that top line, no growth, 0%, we can afford another $10 billion Great Observatory. It fits. And we can even start another one. And even if you come at me and say, well, Webb costs 10 billion, so it's going to cost more than 10 billion. I'm going to come right back at you and say, yes, still, I can still do a Great Observatories program. So I don't buy the mythology that we can't afford to do that with the budget that we have. So that's one point I wanted to make. Next time step. I also said, I'm imagining more than that. I'm imagining more than one in space. I'm imagining more than one in the ground. Can we do that plural? And so the next time step shows you a thought experiment. What if we increased the budget of the astrophysics division by just 2% per year? I'm not talking about doubling it or tripling it. I'm talking about 2% a year. In that case, those blue, orange, and light green bars show you that by the mid 2040s, we could have 3 great observatories flying in space. Is this crazy talk? Let me show you an example of a different division in NASA, next time step. This is the budget from the Planetary Science Division shifted forward 10 years, showing you that after the last decadal survey we did, full disclosure, I was chair of the Giant Planets panel for that, so I had a hand in it. But after that came out, we saw the Planetary Science Division budget double. And there were many, many factors, and we can have a lot of discussion about what those factors are. But my takeaway point from it is that it's not outside the realm of possibility that with a really great imaginative mission set, we can do the inspiration piece that Ellen Stofan talked about in her keynote talk earlier in the day. We can do that. And what about NSF, next time step? Those of you who are in Washington and who have been paying attention know that there's a lot of dialogue right now about the future of the National Science Foundation. There are different visions for it, but many of these visions for the future of the National Science Foundation involve significant increases in the budget for different parts of the National Science Foundation. And so I can imagine, again, this is all in my head, I'm imagining that we can make the argument for robust, large facilities for the United States community, for astrophysics and have those large ground-based facilities as well. So I think that the next time step, my takeaway messages from this, that even flat budgets can get us some really remarkable, powerful tools in the future. Modest growth or even optimistic growth can take us into a whole new realm of exploration of the universe, and that there are congressional discussions taking place right now that will affect these things. So I echo Paul Hertz from NASA when he says, "Carpe posturum," seize the future. I think the future is there for us to seize. I think that this barrier may be one that we can overcome. So that's the end of that spiel. Next, back to you, John.
Thank you very much, Heidi. And I am super excited about the possibilities of enabling these future things and then making them talk to each other to go after this grand question. John, I'd like to get your perspective on this. And oftentimes it's a voice that in the academic circles is not usually heard unless we're actually trying to build these major facilities, which is the critical role of industry in this, Northrop Grumman and other partners. So I'm wondering, what you think about what you've heard so far.
Unmute. There we go. I'm off mute. I'll frame my thoughts here in a couple of flavors. First of all, to follow up what Heidi said about the Great Observatories is yes, exclamation point. And in fact, a large group of us in industry are working to make that a reality and participated in all the decadal mission studies to do that. And we believe if there's the willingness to dream and fund them, that in fact, all of those observatories are not only achievable, but with the right kind of architecture of systems, even more affordable than perhaps even Heidi had posited with, again, a non-stovepiped approach to these missions as a program and not individual bespoke one-on-one. I just recently wrote a paper talking about reusing the Webb design for the purposes of origins. And it could be repurposed elsewhere, recouping investments in spacecraft and leveraging reduction costs in production. The other part of the cooperation scheme or milieu or ecosystem, I think, goes to organization and science, and this is where we need some help for science to be imaginative, as imaginative as John and Eliot with the remote occulter, imagining something that sounds a little outlandish, right? But imagine if you could coordinate ground and space observatories and trigger them to look for various signatures with gamma ray bursts and gravity waves. How could you go back and essentially make the libraries all compatible? So I think there's a fair amount of scientific philosophy and approach and establishing what's the value in doing this work. And I think it will serve to drive the astronomy community together and show a greater science return and convince Ashlee's colleagues to help get us some more resources to do even more great things, right? Because this is, the gateway science to lots of the other physical sciences, which then begins to touch other parts of things the government's interested in terms of national prestige, national defense, economic development, new technologies, et cetera. So I think it's good not only in and of itself, but it can enable other things that people that are potential funders are also very interested in.
Great, thanks, John. Ashlee, I'm going to bring it over to you, and I might pose it as a question, which is, the diagram that you showed with all those different stakeholders trying to interact around perhaps a single science question. How does your committee or how do policymakers take all of that oftentimes collision input and turn that into something that we can use and go forward with?
Sure, yeah, and I think that's a very good question. And as we get into sort of more of the commentary part, I should preface anything else I say, and just with as you might expect, I am definitely not here to represent any member of Congress's view. I'm just representing myself and my observations through my work on the committee, but also elsewhere. But I think John raises an important point, and I want to. The biggest sort of point I'd like to emphasize, and I always want to emphasize, is that the decadal surveys are essential and uniquely valuable, particularly from the astronomy community, even within the scientific community. One way that you can, as John was alluding to, there are many different inputs and players. The decadal survey, the science community does a lot of work. Undergoing a survey, as many of you who may be involved either in the current survey or in previous surveys, those are a lot of effort. A lot of fights happen behind closed doors, as they should be. Scientists get together and make the hard decisions and come out with true community consensus priorities. And that is so valuable on the Hill, and it is used on the Hill. It is cited. It is a law that NASA has to do them. NASA was already doing them, but it was so emphasized that it became a law that NASA needed to continue to do them. And so that gives the community a very big leg up that I think is not always appreciated. The other angle that I will mention is that, and maybe this falls under the myth, is that astronomy has very few, if any, detractors. You see this in the public, but also within Congress. There are few people. There's no one that I know of who's going to make it a plank of their a key issue that they're anti-astronomy. People want to be or love space and love science. It's the challenge to overcome is simply that there are many other priorities. We see this in public polling, and we see in observations just from watching the work of policymaking. If you watch our hearings or hearings on space topics, members across the spectrum are very excited and passionate about space, and particularly about astronomy. A lot of times, it's not that those members need to be convinced why astronomy is important or why the work that you're doing is important. What they are looking for is they're looking for ways that they can then go convince their other colleagues who are not focused on these issues to realize that these are important, that in the large portfolio of work that the federal government does, that these are also important to fund, that when making hard choices, that this should be part of the question. And those justifications and the answer to why can't be quite as simple as just more science. I know that most of us think that more science is good, but even just understanding, being able to communicate why more science is good, or if X or Y is funded, what do we get from that? What is the return from that? What is the value, as John was just speaking about? What is the true value of that to the public, to the scientific community? What can you learn? And how does it connect specifically to these agencies? These agencies have, John spoke about this at the beginning, these agencies have particular mandates, and it's important for policymakers to hear why a certain agency should take something on as part of its responsibilities. How does it fit into the agency meeting its mission, or the agency's, how does it fit with the expertise and the resources of that agency? So being thoughtful about that, both from the messaging, but also from truly thinking about the value and the role of the work. Why are we doing this work other than the simple of just, let's do more science? What do you get? How is this truly improving science per dollar?
Well, I'm going to key in off of that, if I may, and if I could get the next slide, and then maybe the slide after that, please. Which is speaking directly to that yield through the lens of ground space coordination, which is, I'd like to figure out a way not only to enable new things and do more science, because I'm a scientist, more science, Ashlee, more, but also to get that science per dollar yield up. And so through this lens of ground space coordination. So I've got three brief things that kind of go back to my cultural clashes. The first is to consider the ground components and the instrument developments as part of the mission. John gave an example of a ground space occulter system, and that's explicit. Those two must talk to each other. But what I have in mind here is when I think about NASA as a mission-centric agency, and if I think about Paul Hertz, Paul would say, NASA doesn't do ground-based astronomy except for when it does. And by that, he means that mission support from the ground is a critical part of making those missions successful to meet their requirements. And so I take that the next level in terms of coordination and collaboration of saying, let's consider ground components and instrument developments as part of those missions. Develop the ground components tailored to those missions to get a higher yield from both of those facilities, right? The yield will be better if the ground is doing exactly the science that's needed to meet the requirements of the space missions, instead of taking the assets that we have and pushing them to their limits and trying to get the most yield. Instead, on day zero, merging ground and space and having the requirements tied to both components. And we're starting to do that in exoplanets, both with the TESS mission and with the NUID spectrograph and that collaboration between NASA and NSF. But I think this is one way to kind of break that mission barrier, that philosophy barrier. Next slide, please. I think the next one is to upgrade that reward structure. You know, we can learn from other fields outside of astronomy. I mentioned particle physics. But we can also learn from our federal partners and from our industry partners on how to incentivize achievement in this field, right? To go beyond the lone writer of the Nature paper who uses, you know, the H-index to move their career forward. But beyond just the papers and all that stuff, we must value infrastructure to achieve coordination. I mean software here, I mean common software, I mean common architectures, because again, the yield will be better. If we value the infrastructure, we're going to get better infrastructure out. And that means we have to elevate those people who are writing the code or who are building the instrumentation in the same way that we value the people who are getting the end science results. Because if we do that, there's more incentivization in the community to want to build the best machines and to write the best code. Next slide, please. And we must upgrade our data. We're on this path, but we must do better. And coordination is not going to be possible in the next decade and beyond without data that is useful, usable, and quick. What I mean by that is that it's useful. It has to go towards the science question, but it has to be usable. Two different people who work in two different fields, you know, ground data and space data, have to be able to both use that data simultaneously, and it must be quick. Transient astronomy requires that data hit the can in a usable way in very, very short time periods. And that means we have to create, incentivize, that we have to pay for and value, and enforce common open standards. The yield will be better. Again, the science per dollar will be better if all of our data is useful, usable, and quick to the entire community at the same time. So that's the end of my my banding about on these things. I want to open it up to Q&A, or if there's other pieces from the panel who want to riff on these things. I'll ask Jim if there's any questions from Q&A we should address first.
Sure, we got a couple of questions for you. So sticking with that a little bit, you know, the useful, usable, quick kind of thing. One of the questions that came in asked about artificial intelligence and machine learning.
Yeah.
How will those, you know, developments in that area, you know, factor into future planning of you know, the ground and space systems and and research overall?
I can take a stab, but I'll defer mostly to the panel. I think artificial intelligence, particularly in the quick sector. So we think a lot about artificial intelligence for large surveys, which I might let Heidi speak to with the Rubin facility. But on the quick side, when we start to get transient events in the millions per day, artificial intelligence may have to select the ground-based follow-up for us. Human beings may not be able to act fast enough to pick the right one or the right spot on the sky to task a Keck telescope or a large facility or a large space mission and get the answer right fast enough before the event fades away or before the science opportunity is lost. And so the development of those intelligent systems is going to be critical. And we have a lot to learn from other fields, right? One of the downsides of astronomy is we tend to reinvent the code wheel, and we don't necessarily need to do that. Heidi, I don't know if you want to talk about Rubin as an application of this, but.
Yeah, absolutely. For those who don't know, the Vera Rubin Observatory is being built in Chile right now, and it is a large telescope that is going to survey the entire southern sky in 3 days, and then it's going to repeat that and repeat that and repeat that for 10 years. And so it is going to be generating millions of alerts every night for anything that might change in the sky, and then feeding that to computer systems that are going to have to sort through this data, and they will have to be using machine learning and artificial intelligence to be able to work in the kind of rapid time scale that's going to be happening and the huge volumes of data that are going to be coming out. And so that team has already been exploring, and there are other survey telescopes on the ground as well that are starting to explore using these techniques to maximize the scientific output. Now, it's interesting, if you listen to the ML AI panel that took place, I think it was yesterday, I was listening, and they were asked specifically, do they think the astronomical community is ready for this deluge of data? And those young people, to a person, said, we don't quite think they're ready yet. And so there's still quite a bit of work to be done. And as John said, I think it's going to be merging of these communities, the computer science and data science, data analytics communities, especially the young people in those, with the astronomical community to really take full advantage of these new large survey facilities that are coming online.
If I could turn this topic into a question for Ashlee, which is at the policy level. So if I riff on what Heidi just said, which is let's get computer science and astronomy and other things that are leverage, quantum information systems, or even federal partners that leverage high volume computing for national security or various other things. Getting those folks together and speaking on a common level, how is that best achieved in your opinion from a policy level? Because we tend to be hyper siloed, right? I will write a proposal to the NSF that says, I want to develop a machine learning algorithm, which could have been developed by the NSA or the CIA or whatever agency, and is now public domain, but we're reinventing the wheel. How at a policy level do you think we can try to address that duplication of effort?
Well, it's a good question. So there are a number of interagency activities that happen. This is one thing that the Office of Science and Technology Policy, OSTP, is very good at doing, at convening and getting agencies and different folks from different communities who have perhaps shared applications or shared shared roles or overlapping there. And so I think there are opportunities there. I think what you had touched on about not wanting to reinvent the wheel is something important. I think within, say, the NASA community and the NASA science community, the earth science folks, astronomy has a lot of data, but earth science has a lot of data. They are at the point of getting, I think just NASA earth science data is ingesting something like 12 petabytes a year right now, and they are only going to be increasing to much higher than 12 petabytes a year in just a few years. And so I think there are ways to learn from each other. And so the role of policy is to help identify, okay, where are there barriers to interaction? Where do there need to be pushes or to get, say, these communities to work together? Or is it that these communities are eager to work together? There are just barriers to them. And so where are ways that we can enable that? And sometimes that's through interagency activities. Sometimes that's through activities at the national academies, but I think that also happens at the scientific level, at the scientist level, in university communities, in a lot of different communities, because it is looking at, how do you learn from one another, and so yeah, I think it happens sort of at both ends of the infrastructure.
Jim, I want to leave time for another question, but I want to give John a chance because I see his hand up. Well, in fact, I'm not even going to pose a question to John. John, go ahead.
Yeah, I think very quickly, the answer is, of course, yes. If you imagine my, worldwide network of astronomical systems, there's obviously going to have to be some organizing code, and to think of this as some kind of old school code that does things, that's not going to be right. There's going to be lots of value judgments. So this is clearly some kind of AI application. But it goes back to the fundamental question, what does the scientific community want? So I think artificial intelligence is interesting, but we've got to use the natural part to say, where's the best payoff for these fundamental questions? Look at my kind of family tree once we filled it out and say, hey, we're going to address this part or that part of the problem space, and here's what we get out of it, right? And I just can't help but think, to use a word from another area, sensor fusion or fusion of data or fusion of multi-messenger is just not going to get us better physics when we look at a phenomena across not only the electromagnetic spectrum, but the non-electromagnetic one as well. It just, you know, a fourth grade physicist will know that this is the right thing to do. It's just a question of getting that priority. And so that's where I think, you know, I'm poking the science community, and maybe even I'm going to poke the mid-decadal review panel to start thinking about this. Because as we plan for things like a LUVOIR and a LYNX and we need to put these system hooks in now so that they can be done efficiently. So you need the imagination today to affect the systems of the 30s, 40s, and 50s. I'll stop there because we're short on time.
Do you have time for another question?
Yeah, so I think it was Heidi's chart of the funding and the 2% and everything. How do we control the cost of technology development for great observatories, for the flagships, both on the ground and in space? I mean, yeah, go ahead.
Well, I think I want everybody to answer that because it's a really critical question. I'm going to do it with a visual metaphor. So the visual metaphor goes like this. When we developed earlier systems, when we were at the stage of the decadal where we started to think about those things, the proposals for those things were oftentimes this thick. For the great observatories we're talking about, this is the precursor work already. And what I mean by this is that the agency, you know, NASA has invested significant amounts in studying the problem before it's even selected by a decadal survey and putting huge amounts of effort in. And this is for one of those four, right? 1,200 pages worth of work and a huge team of people leading to that answer. And so I think part of the way we control the cost is to really do our homework well before we even select these missions, to understand the science, to understand the trade space. And this was a great experience because the engineers, industry, and the scientists all had to work together to produce that document. And then we understand the risks better. So understanding our risks and building our missions smarter helps constrain that cost. I know John has thought a lot about this. Heidi, Ashlee, all have thought about this, and I want to give everybody at least 30 seconds to respond.
Okay, here's my 30-second pitch then. One of the things we learned about Webb, one of the reasons that the cost ballooned for Webb is that we didn't have the funding in the right years, particularly in the early years. We did not have the reserves that we needed to deal with the problems at that time. Everything got pushed and pushed and pushed to the right, and that just expanded the budget. So starting with a realistic profile, and I think we have a much better idea of what that is, as John has indicated, and making sure we fund that realistic profile the right way from the get-go will get us a long way to controlling costs. That's my 30-second spiel. John?
I'll give you my 30 seconds. I agree with everything that's been said before. I would say we need to consider these not as disjoint programs, but as a series of programs and see what can be leveraged. Again, I alluded to papers that showed we can reuse architectures for different missions. That should be the goal. And if we do that and have a continuous funding stream, we can be more productive and return those great observatories and deliver them to the community.
And I'll just add, I mean, I think it's outlined in lots of folks have looked at this. There are a lot of best practices in terms of managing costs, but it does really, and that is important throughout the phase of development, but at the start, it's about being honest with ourselves and our stakeholders about how difficult something may be, about the cost, about the risks, about the true level of effort, not being optimistic, but being truly honest and finding independent validation for that honesty. And also the important thing that we hear a lot about is about understanding our requirements from the start. And that's connected to the data question. So if you're going to need significant efforts on data management or processing, then understanding that from the very early on in the process, or else you understanding requirements for the mission, for the technology, for mission support, for anything else, setting those early, not just deciding we'll figure that out as we go along, is a really key element.
All right. Well, I think our time is up, Jim, but before you close us off, I just want to thank John, Heidi, and Ashlee for joining us today and for the fun discussion.
Thank you.
I'm muted. Yeah, first time I've done that all thing. So thank you.
Close it right, Jim. Close it right.
Exactly. Thank you, everybody. That was great. That was really a good session. We really appreciate it, and what a great way to end the symposium. So, John, Heidi, Ashlee, and John, thank you so much. Appreciate it. All right, and with that, that is a conclusion to the 2021 Goddard Symposium, but hang on just 1 second, everybody, while we get some of the stuff out of the way. Thank you to all of our speakers and panelists. Thank you very much to our event sponsors: Aerojet Rocketdyne, the Aerospace Corporation, Ball Aerospace, Blue Origin, JHU APL, KBR, L3 Harris, Lockheed Martin, Northrop Grumman, SAIC, Teledyne Brown Engineering, and our media sponsor, Space News. Thank you again for attending. Make sure to check out our future events. The Glenn Symposium is coming up July 13 through 15. We're going to do that one again online. But the Von Braun Symposium will take place October 12 through 14, and we're shooting to have that one in person in Huntsville. So please join us for that one. I would now like to welcome in Alan DeLuna, as well as, if they're all there, the rest of the AAS team who put this on. Just come on in and say hello, get yourself up on screen. Before Alan goes, Sarah, Kelsey, and that's Patrick down there. Thank you so much for all your hard work over the past weeks on this. Really appreciate it. Y'all knocked it out of the park. So with that, I will turn it over to Alan.
So yeah, I'd like to take a moment and thank everybody that participated, that brought us content and brought us planning. Had a great planning team. I really want to thank our chairs, Michelle Teller and Brendan Curry, who they were both brand new at this kind of thing, or not this kind of thing, but brand new at this conference for AAS. And they did a great job pulling it all together, the program and everything. And now for our staff, you guys that are still on, you don't know how much work the staff did. In pre-planning, they went in and had thousands of emails for advertising, where they managed 300 plus registrations. They managed 36 speakers who had to go off and get multiple sets of instructions, and they all had a little rehearsal that they had to do. So our team did a great deal there. And in real time, almost every one of them had at least 2 computers running, 2 Zoom rooms, the event application, the networking lounge, 3 different versions of chats, and an audio bridge where we were all talking together to try to manage this together. Oh, there's the audio bridge. And so a lot goes into making this work, and the staff did a great job doing it. Patrick, thank you. And I will remember, as Patrick tells me lots of times, turn off your mic, Alan, turn off your mic. Always in my ear, turn off your mic. And then every once in a while, we go off and we say, Sarah, I need to do this. And Sarah says, well, I already did it just a moment ago. It's done. So thank you, Patrick and Sarah. Goodbye to you. This is their last full-time conference with AAS. We may have them back for visiting or something in the future, but right now they're going off to do other things. Kelsey Cadlow, I hope you learned everything, because you're going to need to know it. And then Jim Way, the best way I can look at Jim White. Best way to look at Jim White. Not a, oh gosh, what a pun. For those of you that went off fishing when you were kids and you had cans of worms, Jim is the fisherman that had a can of worms, and the worms constantly tried to crawl out, and he had to take and poke them back in the can and push them down with his finger so they wouldn't get up so fast. So he had all the worms to do this time, and he chased all the worms back into the can and pushed them in. So thank you to our staff. Thank you, Jim and Patrick and Sarah and Kelsey. And thank you everybody that attended from AAS. Thank you, and we'll see you at our next conference. Good night.